if rectangular loops carrying current I is situated near a long current carrying wire, if these sides of the rectangle are parallel with the wire, then what will happen to this rectangular loop? So we know that the current carrying conductor always produces a magnetic field, and its magnetic field is like a concentric circle. So the magnetic field of the wire is, we can use the right hand rule. If this is the direction of the current is, and the direction of magnetic field is coming out to this side and entering into these sides. So this means that the rectangular loop is in a magnetic field of a current carrying conductor, which is into this plane, or along the right sides of the wire, the magnetic fields are entering the pages or entering into these pages. So then we can easily see that there is a magnetic force on the current carrying loop or on a rectangular loop due to the magnetic field of the current carrying long wire. So by using the right hand rules, just we can find the direction of these forces. If we take these sides of the rectangular loop, the direction of field is into the page, and we can write the force is simply acting like in this direction. And if we take these sides, the force is acting in this direction. The force makes the loop to rotate in this magnetic field, just like the forces are a couple and they are causing the torques, and the rectangular loop will rotate on the axis which is parallel to the current carrying wire. So this current carrying loop will rotate in the magnetic field of the current carrying conductor. So the correct answer is on alternative D, which says the loop will rotate about an axis parallel to the wire. If the object of mass m enters the magnetic field with the velocity v, and suppose the object has charge q, then if any object is with a charge enter magnetic field, it's obvious that it follows the circular paths, or it performs a circular motion. That is, the magnetic force always makes the object to rotate or to make a circular motion. That means the magnetic force is a centripetal force which makes the object to circulate. So this means that the magnetic force given by, if the velocity and the magnetic field are perpendicular to each other, directly we know that force is q, the velocity of the object is, times the magnetic field strength is q, v and b. So this force is directly equal to the centripetal force, which is m v square over r, where r is the radius of this circle. Then what is the amount of charge of these objects? So since the magnetic field produces the centripetal forces, if we equate this to equation qv, b is equals to mv square over r. Then if I cancel 1v with b, I have qb is equals to mv over r. And if I rearrange and find for q, I get that the charge on the object is given by mv divided by b times r. So this is the amount of charge on the object. So the correct answer is on alternative D. A wire of length L, 0.5 meter, laying along the x-axis carrying the current is of 2.4 ampere in a magnetic field which is laying along the positive z-axis. So the strength of the magnetic field is 1.6 Tesla. Then what will be the magnetic force on the current carrying wire? So we know that the magnetic force on a current carrying wire placed in a magnetic field is given by force is the magnitude of the current or amount of the current is in the wire, the vector length of the wire cross with the magnetic field vector. So L cross B. So we can take L as a vector because the length of the wire is laying along the positive x-axis. So the current is flowing along the positive x-axis. So then we can find that the amount of the current is 2.4 ampere. The length of the wire is 0.5 0.75 meter I cross the magnetic field is 1.6 Tesla K. So this is equals to directly 2.4 ampere times 0.75 meter times 1.6 Tesla, which is I cross K. Then we have left with I cross K here. If we multiply this number directly, we get that this is 2.88 ampere times meter times Tesla is directly it's equal to Newton. And I cross K from the vector analysis. From the vector analysis, we know that I cross K is equals to minus J. So this is equals to minus 2.88 J Newton. So the force is along the negative y-axis. So the correct answer is on alternative C. This question is the same to question number 3. This is the entrance examination of the different years. The same question but in a little bit different ways. That means if the current carrying wire of length this much is laying along the positive x-axis, this is x, this is y, and this is z-axis, and the magnetic field is acting along the positive z-axis, then what will be the forces, magnetic force on a current carrying wire? Exactly, we know that the magnetic force is equal to IL cross B. So this is equals to directly, as we have seen in question number 3, this is 2.4 ampere, length is 0.75 meter, I cross with 1.6 K Tesla. So this is equals to, if you multiply number together, 2.4 times 0.5 times 1.6 is 2.88 Newton, ampere times meter times Tesla is Newton, and I cross K is directly it is minus J. So the force on the wire is 2.88 Newton along the direction of the negative y-axis. So the correct answer according to this question is on alternative A, along the negative of y direction. So the correct statements about the effect and formation of magnetic field is alternative A says a magnetic field exerts a non-zero force on a stationary charged object. So this is force simply because the magnetic force is given by magnetic force on a moving charge is given by Q V cross B, or simply I can say Q V B sine of theta some direction, a unit vector. So magnetic force is 0 simply if V is 0. V is 0 means the charge is stationary. So if the charge is stationary, the magnetic force is immediately 0. So alternative A is not correct, which says there is a force on stationary charged objects. So there is no forces on stationary charged objects. Alternative B says that a magnetic field exerts a non-zero forces on a conducting wire placed in the magnetic field. So the force on a current carrying conductor in a magnetic field is given by force is equals to IL cross B, or I can say IL B sine of theta some unit vector n. So this is only true if theta is different from 0 and 180 degree, because if the direction of the current is or the vector lengths of the wire and the magnetic fields are collinear, this is not true. So the force becomes 0. So the force only exists if the angle theta between the direction of the current is or the vector lengths of the wire and the magnetic field is different from 0 and 180 degree. So this statement is not always true. Alternative C says that a uniform magnetic field can be created at all points around a long current carrying wire. So as we know, a current carrying conductor has a magnetic field around its surroundings like a concentric circle. So magnetic field around the current carrying conductor is like a concentric circle. The magnetic field strength of a current carrying wire at any point is, let me say, this is point P, which has r distances from this wire. The magnetic field strength at point P is given by is mu naught, the amount of current in the wire, divided by 2 pi times r, where r is the distance from the wire to the point is. So as we can see, the magnetic field around the current carrying wire is not uniform, because as we go further away from the wire, the magnetic field strength is reducing. So B is inversely proportional to r. So it is not uniform, it's not constant. So this statement is not correct. So alternative C is not correct, because uniform magnetic field cannot be created around a current carrying conductor. Alternative says that a magnetic field can be created in the space surrounding any charged object that is in motion. So magnetic field is created around any moving charges, because if the velocity of the charge is different from zero, always there is a magnetic field around the charge. If the charge is in motion, moving charge means simply current is, so the current always produces a magnetic effect, or it produces a magnetic field. That means the magnetic field can be created in space surrounding any charged object when it is in motion, or when the velocity is different from zero. So this statement is always true. So according to the question, the correct answer is on alternative D. An electron moving a speed of 1.5 times 10 raised to 7 meters per second enters a region of a magnetic field with strength 2 times 10 raised to minus 3 Tesla. Then what will be the radius of the circle if the electron will follow the circular path in a magnetic field? So as we have seen earlier, the magnetic force is a kind of centripetal forces, which is mv square over r. So then the magnetic field, the magnetic force on an electron in a magnetic field is directly given by F is equals to, so QVB sine theta some unit vector n. But the question says that the electron is entered the region of magnetic field perpendicularly, so theta is 90 degrees and sine of 90 degrees directly 1. So then we can say that the magnetic force is directly equal to the centripetal forces, that is QV P is equals to mv square over r. So if we rearrange and solve for r, r is directly given by mv divided by q times b. And if we solve for r, radius of the circle is m, mass of the electron, the velocity of electron, charge on electron, and the magnetic field strength in which the electron is entered. So this number become mass of the electron is 9.11 times 10 raised to minus 31 kilogram, and the velocity of the electron is 1.5 times 10 raised to 7 meter per second, divided by charge on electron is 1.6 times 10 raised to minus 19 coulomb. It's actually negative, but I take only the magnitude times the magnitude of the magnetic field is 2 times 10 raised to minus 3 Tesla from the given. So if you do this calculation directly, you get that it is 4.27 times 10 raised to minus 2 meter. So it approximately it's 4.3 times 10 raised to minus 2 meter, which is directly equal to 4.3 10 raised to minus 2 is centimeter. So the correct answer is on alternative B, which is 4.3 centimeter. A wire carrying current in a plane of this page toward the top of the page experiences a magnetic force toward the right edge. So the current carrying conductor is laying upward in the plane, and the force on the wire is toward the right edge of the paper. What will be the direction of the magnetic field causing these forces? So we know that the magnetic force on a current carrying conductor is I is equals to always L cross B. This is vector L, and this is the force vector along this direction. So the direction of the magnetic field which is causing this force is perpendicular to both the forces and the length of the wire, or the vector length. So if we cross this vector together, we get the vector perpendicular to both these vectors. So it is out from the plane. So out from the plane means it is indicated by the dot. So magnetic field is outward or out from the page. So the correct answer is on alternative C, which says the magnetic field is perpendicular and directed out of the page or out of the plane of this page. So the direction of magnetic field is out from this plane, and the correct answer is on alternative C. So the torque experienced by a current carrying loop in an external magnetic field is given by torque is equals to the product of the number of turns of the loop, the current carried in the loop, the cross-sectional area of the loop, and the external magnetic field, or the magnetic field in which the loop is laying. So therefore this torque is directly depends on the number of turns. So alternative A is directly wrong. It also depends on the amount of current in the loop. So alternative B is also wrong. And C says it depends on the orientation of the loop. So orientation of the loop means how the loop and the magnetic fields are arranged with each other. That means the angle theta between the area of the loop and the magnetic field B. So this means that the orientation of the loop is also determines the amount of the torque. So this is correct. This is depends on the magnetic field generated according to the Lenz's law. So the magnetic field on which the torque depends is the external magnetic field in which the loop is laying, not the magnetic field produced by the loop itself. Therefore the correct answer is on alternative C. Two long wires of the same length and cross-sectional area carrying the same amount of current correct about the magnetic field and the magnetic force on the wire. So a statement on alternative A says that the magnetic field is zero at a midpoint between the wires where the currents are in the same direction. So we know that if the currents are both in the same direction, current 1 and current in wire 2, so the magnetic field produced by wire 1 is to this side, it is into the page, to this side it is out of the page by using the right hand rule. But the magnetic field produced by the second wire is it is outward or out of the page to this side and into the page to this side if the currents are in the same direction. So we can say that at the midpoint between them, the magnetic field due to this wire or wire 2 is out and the magnetic field of the wire 1 is in. So they are opposing each other, and if the currents are equal and the wires have the same length, the same cross-sectional area, the magnetic field at the midpoint is zero. Alternative A is the correct one. So let's check for the alternative B, which says the force between the wire is attractive when they carry current in opposite direction. So we know that directly if the currents are in the same direction, the wire attract each other, and if the currents are opposite, repel each other. So alternative B is not correct. When you check for alternative C, the magnetic field between the wire reinforce each other when the currents are in the same direction. But when the currents are in the same direction, the magnetic field between the wires opposes each other, do not reinforce. So the alternative C is also not correct. When we check for alternative D, it says the magnetic field due to 1 is proportional to the current through the other wire. The magnetic field of this wire is B1 is directly, we know that it is mu naught I1 over 2 pi r at any point is, and the magnetic field of the wire 2 is mu naught current in I2 2 pi r. at any point is from wire 2. So the magnetic field of wire 1 depends on the current through wire 1, do not depend on the current in wire 2. So magnetic field of wire 2 is also depends on the current in wire 2, not that of in wire 1. So alternative D is also not correct. But the magnetic field on wire 1 is due to the magnetic forces on wire 1 is due to the magnetic fields of wire 2, and the magnetic force on wire 2 is due to the magnetic fields of wire 1. Forces on one wire depends on the magnetic field of the other wires, the forces, but not the magnetic field. So the correct answer is on alternative A. A positively charged of a charge 3.2 times 10 raised to minus 19 coulomb is moving along the x-axis in a magnetic field of strength 0.5 Tesla in a positive y-axis. Then what is a forces on these charges if it is moving with a velocity of 1000 meter per second? So we know that the force on a moving charge in a magnetic field is directly given by Q V cross B, which is equals to, if we substitute the value, this is equals to 3.2 times 10 raised to minus 19 coulomb times, or it is 1000 meter per second I cross with 0.5 Tesla in the direction of J. So if we multiply this number directly, we have 3.2 times 10 raised to minus 19 times 1000 meter raised to 4 meter per second times 0.5, and we have left with I cross J is left. So if we multiply the number together, 3.2 times 10 raised to minus 19 times 10 raised to 4 times 0.5 is equal to directly 1.6 times 10 raised to minus 16 Newton. I cross J is equal to, directly we know I cross J is equals to K, so in the K direction. So the force is 1.6 times 10 raised to minus 16 Newton in the positive Z axis. So this is in the positive Z axis. So the correct answer is on alternative D. So if charged particles enter a magnetic field perpendicularly, it's obvious it always follows the circular motion, or the magnetic field makes the charged particle to follow the circular paths. So this means that the speed of the object will remain constant, but its velocity is changing, because velocity is changing the direction. Velocity is changing in direction. So since the linear momentum of the particle depends on the velocity, it depends on the velocity, not the speed, but kinetic energy depends on the speed of the object. This is the speed, this is the velocity. So speed means here it is the magnitude of the velocity, but the magnitude of the velocity is not changing, but the direction of this velocity is changing. So we can say that since the velocity is changing, the linear momentum of the object is changing, the magnitude of the velocity is constant, so the kinetic energy of the object is not changing with time. So we can conclude that the linear momentum of the object is changing, but its kinetic energy is not changing. But linear momentum is changing only in direction, but not in magnitude. So the correct answer is the linear momentum of the particle change, but not its kinetic energy, and the correct answer is on alternative C. So, which of the following is not correct about the magnetic field? Alternative A says that magnetic field lines are closed. So this is correct always, because magnetic fields are just like a loop. They come out from the north pole of the magnet and enter into the south pole is outside, and also they continues from south to north. It's inside the magnet. So magnetic field lines are the closed loop. So they have no the beginning and terminating points. They have no start and end. So alternative B says magnetic monopole exists. So this is not correct because magnetic pole always exists in pairs. That means north and south. So magnetic monopole do not exist. C says that magnetic field is produced by a moving charge. So this is true because magnetic field is always the result of a moving charges. And D says that the denser the magnetic field lines, the stronger the magnetic field. So this is true. If the magnetic field lines are very closer to each other or dense, they indicate always the strong magnetic field. This is also correct. The not correct statement is on alternative B, so the answer is B.